Hello everyone. In this video, we're going to look at another example on how to study the relationship between two products using partial derivatives. So here we go. So in our example, PA and QA are going to be the price and the quantity for bread. Meanwhile, PB and QA are going to be the price and demand for butter. So QA is going to be modeled as a function of price of item A and price of item B with the following formula. It's 10,000 times e to the power of minus 2 PA squared PB cubed, and QA is modeled by 50,000 divided by the square root of 1 plus PA squared plus PB to the power 4. So what we're going to do in this example, we're going to compute the sign of all partial derivatives. So again here, notice that QA is a function of two variables, PA and PB, and so is QB. It is a function of two variables with respect to PA and PB. So we're going to compute those partial derivative for QA with respect to PA and also to PB. And the same thing for QB, we're going to compute the partial derivative with respect to PA, and also with PB. And of course, as usual, remember this is absolutely crucial. The sign of the partial derivative of QA with respect to PA is going to be always going to be negative, because of course, when you're focused on one product, if you raise the product of that one, the price of that one product, the demand will go down. And it's the same thing for the second product. If you raise the price of the item B, you're going to get a decrease in demand. So we always simply have to verify that the sign of those two partial derivatives are always going to be negative. Meanwhile, the one that we don't know are the other two. What happens when you raise the price of the other product? And this is what will allow us to decide if these two products are competitive or complementary. Of course, if there's a context like here, bread and butter, those two items are typically not in competition. They go together. They're very delicious together. So we are expecting those two products to be complementary, but we're going to verify this with our computations. So let's go with the first two partial derivatives that I like to compute first, are the one where I know the answer. So I'm going to compute first the partial derivative of QA with respect to PA, and then I'm going to compute the partial derivative of QB with respect to PB. And I know these two should give me a function that will always be negative. All right, so for the first one, so let's differentiate QA with respect to PA. So we have 10,000 times e to the power of something. So I have to use a little chain rule here. So when you have e to the power of something, you get, when you compute the derivative, the exact same thing. So let's keep the coefficient. So 10,000 stays. And then since the derivative of e to the something is e to the something, you get that e to the power of minus 2 PA squared PB cubed again. But then you need to multiply by the derivative of the interior with respect to PA. And here the only place PA is at the exponent is that PA squared. And we know that the derivative of PA squared with respect to PA is 2PA. So here, minus 2 is just a coefficient. The derivative of PA squared is 2PA. And then the PB cubed is just another coefficient that you keep. And that's my partial derivative of QA with respect to PA. Now let's just do a little sign analysis. Well, 10,000, of course, is positive. E to the power of anything is always positive. Minus 2 is negative. 2PA, that's positive. Remember, the prices are always positive quantities, and PB cubed will be positive because I have that one negative term. The whole thing, when you multiply these 5 parts, will be negative as expected. So you're expecting that negative value. So that's good. Now for the next one, same thing. I just did some algebraic preliminaries. All my variables were at the denominator in the square root. So we know square root is the same thing as powering by 1/2 because everything is downstairs. That power 1/2 can be brought up as power minus 2. So here I can see again that if I want to differentiate with respect to QB with respect to PB, I simply have to use again a chain rule. I have something to the power minus 1/2. So here we go. So the 50,000 stays. That's just a coefficient. And now something to the power minus 1/2. I'm using my chain rule. The minus 1/2 falls. Remember, the inside never changes. So 1 plus PA squared plus PB to the power 4. And minus 1/2 minus 1 is minus 3/2 times. Now I need to compute the derivative of the interior. Again, now we're doing this with respect to PB. The only PB alive here is the PB4. So 1 will go to 0. PA squared will go to 0 when you're differentiating with respect to PB. And then the PB4, okay, that's 4 PB to the power 3. And that's it for that little chain rule. Now let's do a little sign inspection. So 50,000, again, that's positive, minus 1/2. Oh no, that's negative. 1 plus PA squared plus PB cubed, power 4, sorry. All of that, even raised to a certain power, all of that will be positive. And 4, which is positive, times PB cubed, that's all positive. And then again here, not a surprise, we get that the sign of this partial derivative is negative. Again, in every single question, even if this is now a question with two variables, when you focus on one item, let's say A, and you compute the partial derivative with respect to PA, you're going to get an equation that will be negative. And same thing when you focus on B, when you compute the partial derivative of QB with respect to PB, you're going to get an equation that is going to be negative again. Okay, so you're expecting those two to be negative always. It's the other two that you don't know, and let's do them now. All right, now the fun begins. So let's compute the partial derivative of QA with respect to PB. So what happens when you raise the price of butter? So what happens to the demand of the bread? Okay, so that's the idea here. So we're starting with QA again. So again, here we have e to the power of something, where inside the exponent we have PB. So we're focusing on PB now. So when you differentiate e to the power of something, you get that e to the power of something again. So I'm keeping the coefficient. So it's 10,000 e to the minus 2 PA squared PB cubed. So the exponential term does not change, but now you need to multiply by the derivative of the exponent, focusing on PB now. So you're going to be multiplying by, so let's open a bracket. So the minus 2 is a coefficient, the PA, squared, and now what's the derivative of PB cubed? It's 3 PB squared. And now, so remember, this bracket here is my partial derivative of my exponent with, so I'm doing a chain rule, but I'm doing it with respect to PB now. So it's nice to compare those two partial derivatives just to see the difference between the two things. Now let's do our little sign analysis. So again here, 10,000, that's a plus. An exponential term, as usual, is always positive. Oh no, the minus 2 here is negative, but the PA squared, that's a plus. The 3PB squared, that's another plus. So only one of them is negative, so the whole thing is negative. What does it mean? It means that if you raise the price of butter, you're also going to get a decrease in the demand of bread. And the idea here is what? Well, if you are spending more money on butter, you will have less money to buy bread. And this is why the demand is decreasing. So it does make logical sense. Now let's verify that the other will also be negative, since this is what we're expecting. So again, here I have 50,000. So we're differentiating QB with respect to PA. So we have all our variables are inside that power of minus 1/2 again. So again, I'm going to use a chain rule. So the 50,000, that's just a coefficient that stays. Again, the minus 1/2 falls up front as a coefficient. I'm not touching the inside, which is protected here. So 1 plus PA squared plus PB plus PBQ4. Sorry if sometimes I don't say the right numbers. Okay, so, and then my new power minus 1/2 minus 1 is minus 3/2. Now I need to differentiate. So I'm doing a chain rule. I need to differentiate the interior with respect to PB. Sorry, with respect to PA. So the only PA here is the PA squared. So 1 goes to 0. So be careful here. There's a difference between a term that is alone, a constant, and you differentiate and it goes away, versus a coefficient. Okay, so here 1 goes to 0, PA squared goes to 2PA, and the PB to the power 4 goes to 0, and that's my partial derivative of QB with respect to PA. So again, a small inspection for sign. That's plus, minus 1/2, that's minus. All that stuff raised to the power minus 3/2. I mean, be careful, like a negative power just means that you're dividing by something positive. So it will be positive, and 2PA is going to be positive. So since everything is positive except for one term, the overall behavior, the overall sign of this equation is negative. So this means that if you raise the price of bread, you have less money to buy butter. So that's why the demand is going down. So this means, so the big fat conclusion here, this means that those two products, so here, bread, that's product A, and butter, which is product B here, are complementary. Okay, so in other words, they go together. Okay, so if you raise the price of the other item, you also are decreasing the demand of that that current item. So, and the philosophy of complementary is that you have less money to buy like two essential goods that goes together. Okay, anyway, so for that video, okay, and that section, that's it. That's all. Bye-bye.